So instantaneous reaction rates, this is sort of cut off the tail end of that last video, mainly because I screwed up. So it got its own video. So yay for instantaneous reaction rates, getting its own time to shine. So in an instantaneous reaction rate, we still have the same curve that represents the concentration of the analyte over time, or concentration of the reactant over time, except now we're trying to find the reaction rate at a particular time, not between one time and another, but just precisely at t equals 4, what's the rate of that reaction. To do that, we have to know something about the tangent line at that point. So in this case, we have a tangent line that's drawn. We just need to calculate the slope of that line. All right, and that will tell us what the instantaneous rate of the reaction is versus what the average reaction rate would be. And so we want to be able to calculate, or think about calculating, that instantaneous reaction rate. We're going to do calculate the instantaneous reaction rate for oxygen. Oxygen, this top curve, all right, changing versus time. It's a reactant, so its concentration is decreasing. It has a coefficient of 1 in front of it, and so we need to, or we want to, determine what that is. Now, the nice thing is the tangent line has been drawn, and we've actually been told what the concentrations are. Not always going to be the case. In most cases, you're actually going to have to look at the axes of the particular curve or plot to be able to figure out what that slope would be. But in this case, it's given to us, or it's shown to us, as well as what these concentrations are. But honestly, there's not a lot different in the process of writing or determining the reaction rate with instantaneous relative to average. And so again, we're going to write out the rate expression. It's going to be the negative because it's a reactant and it's going to be decreasing in amount. We're going to be the change of the concentration of oxygen over the change in time. And the factor is going to be 1 over 1, where that 1 in the denominator comes from the fact that oxygen has a coefficient of 1 in front of it in the balanced chemical equation. So if I simplify this or get rid of that fraction, because I can, because 1 over 1 is 1, that is the expression for the reaction rate in terms of oxygen. Now we just need to take a look at this line, and we're going to call this point back here our initial, and we're going to call this point over here our final. And again, it's between 1,000 and 3,000 seconds, but honestly, it could be between any 2 points on that line. Doesn't really matter. And when we call this the final point, all right, our T final would be 3,000 seconds. Our T initial would be 1,000 seconds. And our concentration initial would be the 0.0084. Our concentration of oxygen final would be the 0.0072. And so that will allow us to determine the slope of that straight line that's tangent to that kinetic curve, that oxygen, concentration of oxygen versus time curve at 2,000 seconds. So if we start to plug some of this stuff in, we would say, okay, well, it's going to be minus, and this is going to be the concentration of oxygen final minus the concentration of oxygen initial. And this would be T final minus T initial. And those concentrations would be, the final concentration would be the concentration that's at 3,000 seconds. So minus 0.0072 molar minus the initial concentration, 0.0084 molar. And then we say T final, 3,000 seconds, minus T initial, 1,000 seconds. And now we've got an expression. It's all numbers. It's just doing the subtraction and the division. And you punch it into your calculator and you find that the rate of reaction for oxygen is going to be 6.0 times 10 to the minus 7th molar per second. Instantaneous reaction rate, finding the slope of a tangent to the concentration versus time curve. So that's it. That's all we've got for calculating reaction rates right now. We'll be looking at rate laws next.